So we have recording, and this is about pressure integration of pressure distribution in Excel. We have an airfoil with two-section flap. So let's see a graph of airfoil contour. It's a main section of foil. Second column is for a first section of flap. Like this. And third column is for third section of flap. Is slightly different from airfoil in previous lecture, but this more complex mechanization. And we have this as pressure as contour of this flap. So, and for each array of data, we have pressure, CP, pressure coefficients. And we could look at picture. This is the pressure distribution for main section of airfoil. I swap order to change direction of vertical axis. After I added additional sequence of data for first section of flap. Yeah, I need X coordinate and I need pressure distribution. I can use two array of data, this for example. And I have a data for different angle of attack in last three columns for small angle of attack, and this for big angle of attack, as I remember 12 and 6. So this is pressure distribution. When I move this frame to different column, I see different pressure distribution slightly changed, yeah. And this so accordingly. So this is for 6. When I move this first frame to first column, I see pressure distribution for 12. And there are difference in upper surface. I have a stall point. In this point, there are stall, and pressure rapidly increase to atmospheric level. 0 CP, it's equal to atmospheric level pressure, ambient pressure. Oh, and when I move, so when we integrate this curve, we obtain lift coefficients, and we could do this not only in MATLAB, we also do this in Excel. Can do. So we need only two columns. These columns with point coordinates. I copy to another, maybe for this and this array of data. And we need to decompose this array into upper and lower surface. How we could do this? For this, we also need additional column for vertical coordinates. Yeah, we don't need for integrated, but we need this for separate data into. Look at numbers. There are positive numbers and there are negative numbers. Negative numbers corresponds exactly to lower surface. So when I select negative numbers and delete it. After I draw a plot and look at curve. I look at plot And I see only those coordinates that correspond for upper surface. Maybe I need to delete also this part. This part corresponds also for lower curve. I don't know this or that data. Maybe that. Oh, I delete. So I don't need this data for first part of work. Yeah, I delete. So I have X coordinates for upper curve of airfoil. So I can delete this 40 rows and look at numbers. We have very small numbers, but not zero. So we need to add additional rows. Put here 0 and pressure also 0. And same for this, we put unity and the airfoil and pressure also unity. So now we don't need Y coordinate, Y coordinate, we remove this column and look at this data. This is exactly pressure distribution for upper surface of airfoil. And we need to integrate this curve. So we need an area under curve. And remember, we use a different direction for axis. So I use reverse order. So we just need to calculate this area under curve. How we could do it? Maybe now I need to do small sketch. So this is our x-axis and this is y-axis. And this is our curve. And we need to integrate. This curve represented as numbers, yeah? For any point, we have two coordinates, x coordinates, first column, and y coordinates. And we have same data for second point. So look, for example, at 2 points. These 2 points in this part of integral equal to area between these two slides. And when we connected these 2 points by straight lines, nothing changed. Maybe in a rapidly changed curvature or on very big distance between points, there are changes, but mostly it's true. So equal area for this trapezoidal segment and part of integral. So really we could replace integral by sum. So we just need to divide our curve to trapezoidal segment, calculate area for each segment, and sum it together, and we obtain integral. So look at trapezoidal element. There are two methods. First methods use rectangular trapezoidal. For this method, we need to obtain these values between points. It's exactly mean values between two adjusting points, yeah? And calculate area of this rectangular. So we need to know distance between second points. First and second points is our dx. And we need to know altitude of this trapezoidal element at middle points. and this altitude exactly equal to mean values between y1 and y2. And this, for example, x1 and x2. So area of this trapezoidal element is exactly x2 minus x1. This is our distance between two second points. Multiplied by 1 plus 2 and divide by 2. So it's exactly formula for elementary trapezoidal element. And when we calculate this for each trapezoidal element, we obtain total area of under curve. And we could do this simply in Excel by simply formula. We have a formula and we go to Excel and type this formula into cell. So x2 minus x1. First, multiply by y2 plus y and divide by 2. So, and we have an area for each element. In each cells, we have area of elementary trapezoidal elements, and we need to sum each together. So it's equal. In my Russian Excel, I need a Cyrillic formula, but in your computer's different formula, but pretty simple. So its value equal negative of lift coefficients. So we just need multiply to -1 and obtain a part of lift coefficients generated by upper surface of airfoil. But also we have lower surface airfoil. So we need copy data from first sheet. And only those for negative elements up to these points. So we copy these values. Pay attention, in this part of data, we have different order of elements. And we need to reverse order of element. And we could look at curve. What data we copy. Yeah, it's exactly for lower part of airfoil. And we can repeat similar course of action. We need to, but we start from this part. Okay, this minus this minus this. It's because reversed order of points for different part of curve. After multiply by this plus this and divide by 2. So it's elementary area for this part, and we extend our cells up to end of airfoil. And we have this data. So sum of these cells for lower part of airfoil. I'm not sure whether we need minus or not. When I delete minus, I have positive values. Maybe I need to plot this data and decide need I minus or not. This and this. I think I don't need any minus because most part of curve under axis. So I have positive area, and this first and this last element have negative area. So I don't need minus, and total Cn. This is, for example, Cn up. This is Cn down, and total Cn. Just sum of these two values. So we obtain lift at main section of this high lift configuration. It's equal 2.96. So a pretty high lift. And this calculation done in Excel without any MATLAB. So it's possible for your laboratory work do such calculation in Excel. Just use trapezoidal summation with this simple formula. Second x minus first multiplied by second y plus first and divide by 2. I also put label columns for clarity. So it's all with integration. We also could repeat this action for this second and third element, for this and this small, but it's exactly same formula, similar part of data. In terms of sketch, I think a bit about algorithm. So in this case, we firstly need to decompose single curve because I have single curve as single array of data for upper and lower surface. Yes. And I need to decompose it by two curves, upper surface and lower surface. And what I need to do, I need to look at airfoil Y coordinate. This is a coordinate of points. And when I see that Y coordinate turn from positive to negative, I make a decision. This is a lower surface and we don't need this set of data. And for lower surface, exactly opposite. We use only Y for negative values. Maybe in this region we also use positive Y, but you can identify these points by its coordinate. It's most last point of airfoil. Also, there are problems with direction. Sometimes calculation do from last points to in this direction. Sometimes opposite, start from lower surface to upper surface. So you need to pay attention how sign of y coordinates change accordingly to array. So when you divide CP plot by two curves, you could independently integrate it. Firstly, upper, after lower curve, ADD data together. Pay attention to also to sign for because those curves lay a different side of x-axis and have a different thing of area. This positive, this negative. So when you integrate this part, you need to multiply by minus 1. And this is a plus. So we don't need any sign change in this part, but in this we need to multiply by minus 1. And after I did it together and obtain total lift. It's all about Excel. I think it's pretty simple. Just you need to decompose single curve. This is for case from a CFD computation. I use this data from CFD, not from experimental. You see a very pretty smooth curve is theoretical computation. Experimental points are mostly not so smooth, but you can decompose curve for lower and upper surface when you take a data from plot and put it in different cells of Excel and integrate independently. I think it's all about this topic, and this presentation maybe help you to do a laboratory work. So I think it's enough for now. If you have any questions, ask anytime in Telegram. Thank you for attention.